We got some new bands, yeah, yeah. We got some new bands, we got some new bands, yeah, yeah. Treating these deals like
Time for physics. Hey everyone. So, just want to apologize for the sound quality in the video yesterday. I realized that it's way too quiet when I don't use my AirPods. By the way, if you didn't know, I have AirPods. So today we're going to be reviewing simple harmonic motion, which, as you all are well aware, is the other really big unit we did this quarter besides momentum. So I'm excited to go back and see what we remember. So when we think about simple harmonic motion, the first thing that should come to mind is the period of the motion. And remember that the period is defined as the time it takes for the object to complete one full oscillation. So for a pendulum, that's one full swing back and forth. And for a mass spring system, depending on whether you're vertical or horizontal, it's just one full, I don't know what you would call that, bounce up and down, or one full oscillation back and forth like that. So, equations. Let's start with the pendulum, which is the first type of simple harmonic motion that we learned about. The equation for the period of a pendulum is going to be T equals 2 pi times the square root of L over G. Remember that L is the length of the pendulum and G is going to be the acceleration due to gravity. So 4 notes about this. First, we see that the period of the pendulum and the length of the pendulum are directly related. So if we have a greater length, we're going to have a longer or greater period, right? If we have a smaller length, we're going to have a shorter period or a smaller period. And then we see that the period is inversely related to the acceleration due to gravity. So if we decrease the acceleration due to gravity, right, we're going to have a greater or longer period. And if we increase the acceleration due to gravity, we're going to have a smaller or faster period, right? Okay, also note 2 very important things. It's kind of counterintuitive, but there's 2 things that the period of a pendulum does not depend on. First, the period of a pendulum does not depend on the mass of the pendulum. That's a big one. And then second, the period of the pendulum does not depend on the angle of release. So if you're in the same location, right, as in you have the same acceleration due to gravity, and you have the same length of string, no matter how far you pull the pendulum back, no matter how much mass you put on that pendulum, the period will not change. And then remember that we have a totally different equation that we use to calculate the period of a mass spring system. So that equation is going to be T equals 2 pi times the square root of M over K. So here the period is directly related to the mass of the system and inversely related to the spring constant, right? So if we have a stiffer spring or a higher spring constant, we're going to have a faster period, right? If we have less mass, we're going to have a faster period. If we have more mass, we're going to have a longer period or a slower period, a greater period. So one example of some type of question that you might get asked is, how does the period of this pendulum and how does the period of this mass spring system change if we increase the acceleration due to gravity? And the answer is that the period of the pendulum would decrease because of that inverse relationship. And then the period of the mass spring system would not change because the mass spring system's period does not depend on the acceleration due to gravity. Or they might ask you what happens when you increase the mass. The only one that would change is the period of the mass spring system, right? So that mass spring system's period would increase. Okay, so let's try a quick example problem. Go ahead and pause the video here and attempt this problem on your own before seeing the solution next.
Yeah, pull up in a brand new Porsche, followed by a matte black van. Yeah, yeah. Never sit by the door, my boy got a matte black fan.